Good morning, everyone. Today, I will present our work on three-dimensional trajectory design for energy-efficient UAV-assisted data collection. This is a joint work with my research collaborators and my PhD students. In this presentation, I will start with the background and the related work, followed by system model. I will then explain the problem formulation and our proposed solution. Then I present numerical results, finally conclude with our main findings and future research directions. In a UAV-assisted communication system, we can generally distinguish between rotary wing UAVs and fixed-wing UAVs. For rotary wing UAVs, research has mainly focused on communication performance, for example, throughput, delay, and energy consumption. On the other hand, for fixed-wing UAVs, there are also studies that optimize terminal-related performance. For example, people minimize the energy consumption at user end or maximize the throughput of the entire system, minimize the delay for data transmission, and also try to extend the flight duration and the range for the UAV. However, when we look at the UAV itself, there has been relatively little work on minimizing its propulsion energy, especially when we consider three-dimensional trajectories. Well, this is the typical case we should consider. This lack of a realistic three-dimensional propulsion energy model actually motivated our research work. So in this presentation, we focus specifically on developing such a model and using it for energy-efficient trajectory design. Now, this is our system model. In our system model, we consider a fixed-wing UAV that flies from a starting point to a final point within a limited time duration denoted by capital T. During this flight, the UAV would collect data from multiple sensor nodes on the ground. Each of the sensor has a fixed location and also a certain amount of data to be transmitted. The amount of data to be transmitted is specified. To model the UAV's movement, we divided the total flight time into discrete number of time slots. At each time slot, we define the UAV's position, velocity, acceleration, all in 3 dimensions. This basically allows us to capture its full 3-dimensional trajectory, as shown in the figure on the left-hand side of this slide. For communication, we assume a line of sight link between each sensor and the UAV. This channel gain is then determined by the distance between the UAV and the node at each time slot, and also based on the standard path loss model for space 3-dimensional propagation. So this system model forms the foundation for our trajectory optimization problem and the solution. Another part of the system model is the data collection model. In this case, we adopt a TDMA protocol, time division multiple access protocol, which means the sensor nodes upload their data to the UAV in separate time slots within each scheduling interval. We let tau k to represent the offloading time allocated to sensor node k in slot I, and the total allocated time across all nodes in a slot cannot exceed the slot duration or length delta, as shown in the inequality 2. The amount of data transmitted from one sensor node to the UAV in each time slot is given by the inequality 3. Basically, this inequality depends on several factors. For example, the emission energy of the sensor nodes, the system bandwidth, the noise power at the receiver end, the offloading duration, and most importantly, the distance between the UAV and the node. Finally, in Formula 4, each node must upload enough data so that its total transmitted data across all time slots meets or exceeds its required data load. So this model captures constraint and the requirements of the data collection, and it connects directly with how we plan UAV's trajectory. In addition to the data collection model, we also define a 3-dimensional mobility model for the UAV. The UAV starts at an initial position and velocity, and must end at a specified final location and velocity. Its trajectory over time is described by the location, velocity, acceleration updates given in Formula 7 and 8. We also impose physical constraints to make this model realistic. The altitude of this UAV must always stay within a minimum and a maximum bound. The acceleration is limited by a maximum value. The velocity must remain between a minimum and a maximum speed. To ensure feasible flight, the pitch angle of a fixed-wing UAV is restricted so that the UAV does not exceed its maximum climb or descent capability. Altogether, these constraints capture the real-world limits of UAV flight and ensure that the optimized trajectory is not only energy efficient, but also physically achievable. One key contribution of our work is the development of a new three-dimensional propulsion energy model for fixed-wing UAV. On this slide, Llama 1 shows the formulation of the propulsion energy when a UAV maneuvers in three-dimensional space. The total energy depends on the UAV's velocity, acceleration, altitude at each time slot. The last two terms in this formula or model, highlighted in the red box, represent the difference in altitude and velocity between the start and end points. Given fixed starting and ending conditions, these terms remain constant. So this new model faithfully characterizes the propulsion energy consumption of UAVs in three-dimensional flights, which is more accurate than the existing two-dimensional model. As a matter of fact, the conventional two-dimensional propulsion energy model becomes a special case of this formulation by setting the vertical acceleration, velocity, displacement to 0. This improvement allows us to better capture the real-world energy cost of UAVs operating in three dimensions, and which is very crucial for the designing of efficient flight trajectories for UAVs. Now, we have defined our system and the propulsion energy model. We move on to define our problem formulation. The objective of our study is to minimize the UAV's propulsion energy as it flies from the starting point all the way to the final point. We collect UAV's positions, velocities, accelerations across all time slots into the optimization variable set, which is M. The initial formulation shown in problem P1 is a non-convex, unfortunately. This non-convexity mainly comes from the terms involving acceleration and velocity in denominators. Directly solving such a problem will be very challenging because of the non-convexity, as well as coupling between variables. So to solve this problem, actually we use two key techniques. One is a variable substitution. The other one is a successive convex approximation, also known as a SCA. Specifically, we sort of introduce auxiliary variables such as lambda I to handle the acceleration terms. We also introduce additional variables xi, theta, eta to handle the non-convex denominator of the terms. Here we show how this successive convex approximation or SCA is applied to make our problem more solvable. At each iteration of this algorithm or SCA process, we approximate the non-convex terms with their first-order Taylor expansion around the current local point. For example, the difficult term involving 1 over theta I is upbounded by a linear function as shown at the top. So by doing this, the objective function can be convexified, resulting in a new form of a problem shown in equation 18. Likewise, SCA is utilized to convexify several non-convex constraints, including constraint 13, 16, and 17. The convexified version are given in 22 through 25. So the important point here is that by applying SCA iteratively, each sub-problem becomes convex and therefore mathematically tractable. Over iterations, the algorithm gradually improves the solution and converges to a stationary point that satisfies the KKT conditions. So these steps essentially transform a highly challenging optimization problem to a sequence of solvable sub-problems, making our three-dimensional trajectory planning practical and achievable. After applying successive convex approximation, the original non-convex problem now is fully transformed to problem 1.3. The objective function from 18 replaced the original non-convex one. The difficult constraints are replaced with their convex version 22, 23, 24 to 25. Now the resulting problem is fully convex and can be efficiently solved or resolved using standard solver like a CVX toolbox. At the bottom, we outline the SCA-based algorithm we designed to solve problem P1. The process begins with initialization of variables and then repeatedly solve the convex problem P 1.3. Update the solution and iterate until convergence. The iteration is guaranteed to converge to a KKT point, ensuring the final solution satisfies the necessary optimality condition. So our solution or our algorithm in this sense is a local optimal solution or algorithm. In terms of convexity, the algorithm has a polynomial order, especially on the order of IC times n to the power of 4.5. So this is computationally tractable for the problem we are thinking of. So this completes the solution framework and allows us to obtain energy efficient three-dimensional trajectory. In addition to optimizing the UAV trajectory, we also actually optimize the transmission schedule of sensor nodes. So the objective here now is to minimize the combined energy efficiency or energy consumption, that is both the propagation energy of the UAV, transmission energy of the ground nodes. So we formulate this as problem P2. The variables now include the UAV's motion parameters, as well as the transmission times, data loads, emission energies of each sensor nodes. Again, this formulation is non-convex due to the data rate constraint and the coupled variables in denominators. To address this, we use the same strategy as we used in the first part of this presentation, which is variable substitution and successive convex approximation. For example, we can replace the logarithmic data rate constraint with a more manageable form using an auxiliary variable gamma, as shown in 28A and 28B. And the key takeaway here is this joint optimization balances the energy efficiency of the UAV with the communication efficiency of the ground sensors. So give us a solution to UAV assisted data collection. Now we take a look at the numerical results. We set up our system with parameters shown here, including flight duration, maximum or minimum speed, acceleration limits, altitude bounds, and the starting and final positions of the UAV. We evaluate 4 different scenarios, including 2-dimensional trajectory optimization for propulsion energy minimization, 3-dimensional trajectory optimization for propulsion energy minimization, 2-dimensional trajectory for joint transmission scheduling, focusing on both the propulsion energy and the communication energy, or 3-dimensional trajectory with joint transmission scheduling, which is our full proposal. So on the right-hand side of this slide, we compare the trajectories of these 4 scenarios. The dashed black curve shows the optimized 2-dimensional trajectory, while the solid red curve shows the optimized 3-dimensional trajectories. We can see the 3-dimensional paths make better use of the altitude dimension to reduce the energy. So overall, our results show the 3-dimensional trajectory design achieves around 10% energy saving compared to the state-of-art 2-dimensional designs. This demonstrates incorporating 3-dimensional mobility is not just a theoretical improvement. Actually, it brings tangible energy benefits for UAV-assisted data collection. Now, this is our conclusion. First, we derived a new 3-dimensional energy model for fixed-wing UAV, which captures the real-world energy consumption more accurately compared to existing 2-dimensional model. Second, we convexified the model and designed energy-efficient 3-dimensional trajectories using a number of transformations and approximations. Our solution converges to a solution satisfying KKT optimality condition, which means it's mathematically sound and reliable, and also practically efficient or effective. Third contribution is actually we apply this model to optimize not only the trajectory of the UAV, but also its data collection schedule. So ensure both propulsion and communication energy are considered. The fourth contribution is our simulation show the significant energy saving about 10% when compared to the whatever best possible 2-dimensional trajectories. So demonstrate the benefit of moving trajectory design from 2-dimensionals to 3-dimensional, yes. For our future work, we plan to extend this framework to address UAV-based secure and energy-efficient data collection, so the broaden application of this particular design to some more challenging scenario. Thank you. That's the conclusion of my presentation.